All right. So let's quickly summarize what we did last couple of sessions. Just two sessions we had, one and a half or 1 hour 45 minutes. So what we learned was that when we talk about mechanism in organic chemistry, okay, there are different ways reaction can happen. All right. When you look at the reaction, you need to identify which of these four or five ways reaction might be happening. And once you guess it right, whether it is SN1, SN2, E1, E2, free radical mechanism, if you guess it, then there is extremely high chance that you'll get the answer correct. All right. So, unfortunately, there are at least 7 or 8 ways the reactions can happen in the organic chemistry. But good thing is that these 7 or 8 ways, if you understand really well, it can cater to infinitely many reactions. So that is why we are doing this. So these type of reactions broadly you can classify into 3 or 4 types: substitution, elimination, addition, right? And substitution are typically of whatever we have learned last two classes that is related to substitution, right? So first we discuss about SN1 reaction, right? SN1. Can anybody talk about SN1? Whatever you may have understood, feel free to speak about it. Anyone?
There's formation of cation in SN1.
Okay, there is a formation of carbocation. What else?
Sir, it's a two-step reaction.
Two-step mechanism. What else?
So they can undergo rearrangement to gain stability.
Rearrangement of the carbocation. All right, the rearrangement can happen. Then, out of 3 degree, 2 degree, 1 degree, which has a higher chance of SN1?
3 degree.
Agree.
3 degree. Out of Ri, RCl, RBr, RF, which one is highest chance of SN1?
Ri.
Ri, because leaving group should be a good leaving group. Otherwise, carbocation. Now, how does carbocation gets created? Is the nucleophile creates a carbocation or it creates on it itself?
By itself.
By itself. Just like when you dissolve NaCl into water, Na plus and Cl minus gets created by itself, right? Same way, due to polarity of the bonds, when you dissolve this in a polar solvent, then in SN1, carbocation gets created on its own, right? What is a typical nucleophile here? Solvent itself is a nucleophile. Typically, solvent itself is the attacking reagent, typically. All right. So if you dissolve Ri into water, what will happen? If it is SN1, alcohol can get created on its own, right? Now, how you will ensure that the alcohol, this alcohol, let us say, if you have this alcohol undergoes SN1 reaction, how will you ensure that? So Diksha, switch on your webcam. Huh. How will you ensure that this will undergo uh, the reaction, SN1 reaction?
OH will it undergoes solenosis where H attaches to OH and that's a good leaving group and it leaves and then
Right,
the nucleophile will attach.
correct. So OH by itself is not a good leaving group. So in case of alkyl halides, the I minus Cl minus, they are stable, so they come out on its own. OH minus, oxygen to carbon bond is very strong as such. So it is not a good leaving group. You need to first make it a good leaving group by ensuring that there is an acid that attacks OH. Okay, this is an example of catalyst based reaction. There's a catalysis that is happening here. Okay, so H minus is increasing, H plus is increasing the rate of SN1 reaction. So this is OH2 plus. And now this OH2 is a good leaving group. And hence carbocation gets created like that. Okay, so this is what it is, right? This is the SN1 reaction. So you know how it is, right? Now let's talk about SN2. Acha, before SN2, what about the stereochemistry here?
So this is a racemic mixture.
It is near racemic. Which one will be higher in value or percentage? Inverted product or retented product? Retention or inversion?
Retented products, sir.
No, it is inverted. Because this I minus, when it is about to leave, it is very near to the R. And in that process only the nucleophile attacks. So nucleophile doesn't want to be near negative charge, I minus, Cl minus. So it tries to attack from behind initially. And once I minus leaves, then it can attack both ways. So retention is lesser than inversion. Okay. SN2, we'll quickly do that. In SN2, first let's talk about stereochemistry. Inversion happens mainly, right? Now, how will you know that with a particular nucleophile SN1 will happen or SN2 will happen? By looking at it, how will you know that?
So if the nucleophile is
File
strong,
is
it will
strong.
undergo too.
Nucleophile is very strong. So it requires a strong nucleophile. The solvent is not a nucleophile. In the solvent, there is KOH, NaNH2. These things are the attacking reagents are dissolved in smaller quantities in the solvent to attack and create SN2 reaction, right? Now, this over here also, you can say that Ri, RCl, this is how it is because leaving group leaves that will always accelerate the reaction. Then it is a one-step reaction. One-step reaction. So when nucleophile attacks, the bond is formed and broken at the same time, right? So there is a complex that gets created. Uh, Let us say this is how it is. This is what it is. Then a nucleophile comes, it attacks here, and this leaves. All of this is happening simultaneously. Now, if it is happening simultaneously, can this nucleophile come and attack from here? Nucleophile is typically negative charge or it has a lone pair, and this is an electronegative thing, electronegative atom. So nucleophile want to be as far as electronegative atom if it is there at the time of reaction. So that is why in SN2 inversion happens. So nucleophile will attack from 180-degree behind wherever the leaving group is. So inversion happens. Okay. Now you can see there is a lot of crowding is also going on, because at the same time nucleophile is also attacking, leaving group is also there, everything is happening together. So SN2 doesn't like crowding, and that is why, here 1 degree SN2 reaction is faster than 2 degree, faster than 3 degree. Okay. I hope you understand very clearly difference between SN1 and SN2. There is no carbocation formed in SN2. There is no question of rearrangement. Nothing. Okay. Now, what we learned next was SNI. Remember SNI? What it is? What was that? Anyone?
Sorry, the nucleophile substitution.
That is internal nucleophilic substitution in a way, but actually, it's not that step. This is typically with SOCl2 or COCl2. So there is a sulfur which has vacant orbitals in SOCl2. Sulfur has a vacant orbital. So this lone pair attacks the vacant orbital. All right. And this Cl goes away, right? Then you will see this is the intermediate that get formed. ROSOCl. There is H also. So that is why there is positive charge over here. Then this H will leave. Now, till now, there is no nucleophilic attack on the alcohol. In fact, alcohol was a nucleophile for SOCl2. This lone pair was attacking sulfur. Are you getting it? The lone pair of oxygen was attacking sulfur. So alcohol was a nucleophile till now. Now you will see that although this mechanism is not very important, but you should understand that such kind of thing you will see later if you study higher order organic chemistry. This lone pair will shift here and create SO2. This Cl minus released, and this Cl minus will attack R. This is intermolecular attacks. So this is RCl plus SO2 gets formed. So you can see that Cl minus comes from the same molecules it comes and attacks the R. So that is why it is SNI. Okay. Little weird, but this is what it is. Then we discuss about what? We discuss about, you remember SN2AR? We discuss about nucleophilic attack on the benzene, right? To typically benzene doesn't have a nucleophilic attack. In order to accelerate that, what we do, anybody remember? In order to augment the SN2 mechanism in aryl halide.
High
NO2.
temperature pressure.
Yes, if it is, let us say, if you are talking about this, and you just directly want to introduce, then you require a very high temperature and pressure. Okay, why it is so? Because due to mesomeric effect, this has a double bond characteristic. This one has a double bond nature, so it will not come out. This is, let's say, the allyl or sp2 hybridized carbon chlorine bond. So that is second reason. Main reason is that it has a double bond characteristic. Okay. Now, if I want it to be happening during in the room temperature, then what condition should be there?
Electron
So
withdrawal.
NO2. Yeah.
Electron withdrawing group should be there. Where? In which locations?
Ortho.
Ortho para position.
Ortho or para position. So if you have more electron withdrawing group or ortho or para positions, then the nucleophile can attack easily because the intermediate that get formed, it has negative charge. So electron withdrawing group will stabilize it by, by not letting it localize in one location. So electron that get generated during the attack, it can disperse itself. So this is the reason why electron withdrawing group is required for SN2AR reaction. Typically, benzene will give electrophilic reactions. Uh, Electrophile, which is, let's say, positive charge, will attack the benzene ring because benzene ring is typically electron rich. It has entire cloud of electron at the top, at the bottom. So a positive charge entity can easily attack. But a negative charge entity like nucleophile, if it has to attack, it should have electron withdrawing group, which will decrease the electron density in the benzene. Otherwise, it will not be able to attack. You require extremely high temperature and pressure. Okay. Then we also learn about the benzene mechanism. These are all, you just need to know a little bit about it. When we will learn about the benzene in detail, you will see that later on. Then towards the end, we learn about the SNTH. You remember SNTH?
Tetrahedral intermediate.
Tetrahedral intermediate. Typically, it is formed when? It is typically formed
So for
Carbonyl compounds.
carbonyl. Very good. For carbonyl compounds. Okay. What is a carbonyl compound? C double bond O. So let us say this is the thing. L is a leaving group. This is a carbonyl compound. And this is the nucleophile. This is, uh, you can easily guess where nucleophile will attack because this oxygen is electronegative. It will pull the electron density due to the minus I effect, and that carbon will be delta plus. This is delta minus. So nucleophile has extra pair of electrons, so it will attack this carbon. But carbon cannot have 5 bonds. So which bond is weakest and to be broken? Pi bond. So this pi bond will break and negative charge can go to oxygen. Oxygen can hold the negative charge because it is electronegative. This is what will happen. And every time there's a carbonyl group, there is a C double bond O and a nucleophile attacks, whether it is aldehyde, whether it is ketone, whether it is acid, you will see the same mechanism. So what we are learning is going to help you in all the chapters that are going to come. So you should understand how it happens. So nucleophile will attack the carbon, and then what will happen? It will have suddenly 4 bonds. 4 bond as in it will have the tetrahedral nature. This is the nucleophile, this is L. Now what will happen is that this negative charge will again come and form a pi bond, and this leaving group leaves. Okay. And instead of leaving group, you will end up having the nucleophile. This is what will be formed. Now, of course, in this mechanism, carbon to leaving group bond should be weaker than carbon to nucleophile. Otherwise, why it will happen? Okay. So this is the summary of what we have done in the last 2 sessions. Okay. Today we'll talk about the elimination reactions. Okay. This is all substitution. Of course, there are maybe some finer details here and there, but more or less we are done with the substitution. So whenever substitution happens, one of these mechanisms we'll be utilizing. Then now we are going to talk about the elimination. Elimination, there are 2 kinds of mechanisms, E1 and E2. Substitution broadly, you can say that majority of the substitution is either SN1 or SN2. Similarly, majority of elimination is E1 and E2. Now, uh, looking at the substrate, looking at the solvent, looking at the reagent, nobody is going to tell you whether it is SN1, SN2, E1 or E2. You need to think and recognize, okay, elimination will happen here. No, substitution will happen here. So you need to pay attention to the reagent, kind of reagents and the solvent. Okay, so let's proceed. Write down even reaction. Okay. So let me show you a typical elimination reaction. So this is the typical elimination reaction. This is halogen. I'm most of the time I'm using halides because halides are very good leaving groups. So almost 50% of alkyl halides will be over by the time we'll finish the reaction mechanism itself. So X is a halide. This. Okay. In step number 1, carbocation gets created. This leaves. Okay. Right. In step number 2, the electrons of this carbon hydrogen, they come here to form a pi bond and H plus is released. Okay. This is what you can see. Okay. We'll we'll discuss how and why it happens, but this is the even mechanism. What happens? First, the leaving group leaves, carbocation gets created, and then H is extracted, H plus is extracted, H plus is gone, but the electron between carbon and hydrogen, 2 electrons, because of that bond, will get paired and create carbon-carbon double bond. Okay, this is the mechanism. Now you can see that the first step, the step 1, do you recognize it is same as SN1? It is exactly same. So since it is same, the rearrangement can happen. Please write down in E1, rearrangements are possible. Very well. But the step 2 is not same. So what makes, how will you know whether in step number 2, substitution will happen or elimination will happen? That is what is the game here. You need to understand that, right? So we'll write all the details. In fact, the first step, please write down. First step, it is a slow step. In SN1 also, that was a slowest step, formation of carbocation, right? All right. In the second step, there's abstraction of proton. I mean, H plus is proton only. Electron is gone, so only one proton is left. So you either call it H plus or proton. It's very, very small. This thing, size of a proton is H plus. Okay. Anybody has any doubt? Anyone?
No, sir.
Now, the step 1 is same. Step number 2, what is happening is you can see that the entropy has increased. Entropy increases in case of the elimination. Why entropy increase? Because the more number of products. Alkene is there, H plus is gone. There is more chaos over there. Many things are coming out, right? So when entropy is increasing, then what is that condition that favors increase in entropy? Increase in entropy means E2, sorry, E1, elimination is going on. Decrease in entropy means substitution is going on. Substitution is what? There are two, three reagents that get substituted. So entropy went down. In elimination, things are coming out. More numbers are getting created. So entropy is increasing. So tell me, at higher temperature, more entropy is favored, or at a lesser temperature, more entropy is favored?
Higher temperature, more entropy.
You can just take an example of evaporation, right? When you boil the water, the entropy increases lot more. So here also, I mean, if you want to understand using thermodynamics, you can write delta G, gives free energy, delta H minus T delta S. Okay. So now gives free energy, you guys remember or not? So if delta G is negative, means reaction will happen. If delta G is positive, means reaction will not happen. This delta H accounts for the thermodynamic variable, as in the product is more stable or not. That is delta H. Okay, but many reactions are endothermic in nature. Many reactions are endothermic. Then also they happen. They happen because this particular thing, T delta S, this T delta S compensates for stability. So that is why in endothermic reaction, if you increase the temperature, the reaction will proceed in the forward direction. Okay, the products are less stable, but still it is getting formed. So basically, I mean, I don't want to tell you unnecessary many complicated stuff. Because of increase in temperature, the delta S is positive for the elimination. So if you increase the temperature, T delta S term increases. And because of that, delta G becomes more and more negative. And hence reaction is favored for the elimination, right? So if you just want to remember like a thumb rule, at higher temperature, elimination is favored. Okay, so if I draw a delta here, it means I am heating it up. And when you heat it up, this delta symbol is there along with some nucleophile. Assume elimination will happen. Is it clear to all of you? Anybody has any doubts? No doubts, right? No doubts, right? Can you draw the energy curve of this for E1? Quickly draw that curve. Try. Then all of you, in this how many intermediates are there, assuming rearrangement doesn't happen? How many intermediates? Carbocation is the only intermediate. If there is one intermediate, there will be two transition states. Okay, two intermediates, four transition states. Double the number of intermediates transition state. Transition states has the highest energy. So using that rule, you can draw it and it will look similar to your SN1. This is your this is your intermediate. These are your transition states. Transition state 1 is when the leaving group bond is getting broken. It is in the process of breaking. Leaving group is leaving. That process of leaving is a transition state. And the second transition state, the second peak is when the this thing, when carbon hydrogen bond is breaking. All right. Okay. So now over here, what do you think is a nucleophile in S? I'm sorry. Another thing that you will notice is that in SN1, the solvent is a nucleophile. In even typically it is not. Okay. But anyways, the main differentiator is the delta sign. The delta sign. In even, the nucleophile act as a what? Anybody guess? Nucleophile act as, what does it act as? Nucleophile does what? Where it attacks? Where the nucleophile attacks? Look at this.
Adjacent carbon atom.
No.
Wait, no, nucleophile doesn't attack.
Nucleophile attack, that is in substitution. In substitution, nucleophile attacks carbon. In elimination, nucleophile attacks where?
Hydrogen.
Sir, hydrogen.
Hydrogen. Hydrogen. It attacks hydrogen to extract H plus. Now, who extracts H plus? What do you call it as? What do you call something which takes H plus? Who takes H plus? I think
Space.
Sir, oxidation.
base. It is base. Okay. So in elimination, it's about base. So sometimes they will write a strong base, stuff like that when elimination is happening. So always remember, substitution, nucleophile attacks carbon, elimination, nucleophile attacks hydrogen. Okay. Now, it is possible to have more than one product. It is quite possible. All right. So can you tell me over here? I'll just give you a simple example right now. This is a situation. Tell me what will happen? Substitution, elimination.
The elimination.
Elimination.
Elimination will happen. Draw the two products that can come out. Two products that can come out. Acha, by the way, whatever elimination we are talking about till now is, it's beta elimination. Beta elimination or 1,2 elimination. Why we are calling it so? Because the leaving group comes from the first carbon and hydrogen is going out from the adjacent carbon. It's not that leaving or hydrogen group are attached to the same carbon. They are attached in two adjacent carbons. One carbon leaving group comes out, other carbon hydrogen comes out. So that is why it is called beta or 1,2. There are 1,1 elimination, 1,3 elimination also, but we will focus on 1,2 elimination only because that happens majority of the cases. Huh. Have you drawn? How many adjacent carbon you can see to this?
Oh, sir.
4.
Yeah, 4.
Adjacent to this 4. This is chlorine.
3, right?
3. But aren't these two exactly same? Whether you go this way or that way, the path is same. So uniquely you can say 2. So it can happen. Let me. It can happen that hydrogen can come out from here or from there. You can say, sir, from here also hydrogen can come out. It is same thing as hydrogen coming out from here. All right, it is the same thing. So if hydrogen comes out from, let me name it 1, 2, 3. If it comes out from 2, what will happen? You will get this type of alkene. Can you see that? This is what you will get. But if hydrogen comes out from here, you will get this. This one. This one is less substituted alkene. This one is more substituted alkene. Which one is more stable? Less substituted alkene or more substituted alkene? Which one is more stable? You have learned in alkene, right? Which one is more stable?
More substituted alkene.
More substituted alkenes are more stable, typically. Now, why so? Because of the hyperconjugation. Because the there is an overlap of sigma orbitals of this carbon hydrogen bond with the pi orbital of this carbon carbon. So there is an overlap. So why these overlap create stability? Because the charge is always unstable if it is located at a very small place. If you let it spread, charge is stabilized. Concentrated charges are unstable. So when overlap happens, the electron gets space to move around. So when it does that, it becomes stable. That is why benzene is very stable, right? There is a pi cloud, electron can move around here and there. Anyways, so this one is more stable, more substituted. So we call this as a Hofmann product. You remember? Have you ever heard these things? Hofmann, Sadjeff.
Yes, sir.
Sadjeff. I mean, pardon my spelling. I don't know. Okay. So, in this even mechanism, the Hofmann product is always more. Okay. Why? Because typically, from carbocation, it gets time and it will move towards the more stable product only. Okay. Fine. So let me ask you the some questions. The first question is theoretical question. So all of you hear it and you answer then. Okay. Correct statement for even reaction. Option A, it is a two-step process. Option B, rearrangement is possible. Option C, good leaving group favors E1. Option D, all of these.
All of them.
Option D.
All of these. Good. All of these. Okay. Uh, let me give you another question. There can be little tricks involved. Okay. So be attentive there. Which one gives three alkanes after dehydrohalogenation? What is dehydrohalogenation? This is dehydrohalogenation only. E1, what we did. Hydrogen is removed. De dehydrogenation. Halogen is removed. Dehalogenation. So dehydrohalogenation. Hydrogen and halogen both are gone. That is dehydrohalogenation. Okay. So your options are CH3, CH2, 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 Br. I mean, I'm not asking what is a major product. Whatever may be percentage of product, which of them gives three products? CH3, 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 Br, CH3, CH2, CH, Br, CH3, CH3, CH2, CH, Br, pH. Try. We can name it. This is first, second, third, fourth.
So option 4.
Others?
So option 4.
Are you sure? Let's see option 4 what happens over there. So CH3, CH, H, CH, Br, and this is phenyl. So which hydrogen can come out? This one. Can any other hydrogen can come out other than this? Any other comes out other than that? Adjacent to this carbon is what? This one or phenyl? Can phenyl hydrogen come out? Can hydrogen from that phenyl group comes out? Huh? Who said 3? Answer it, no. This is a phenyl group like that. There is hydrogen over there, no doubt. There is a hydrogen, but this hydrogen, wait, 1, 2, 3, 4. No, it doesn't have a hydrogen at this location. So only one hydrogen can come out. Do you all agree? Only one hydrogen. I mean, even if hydrogen would have been there from benzene, sp2 hybridized carbon, hydrogen will not come out. Okay. Now, if this hydrogen comes out, how many products you will see? How many products would be there? 1, 2, 3. How many?
One.
1?
One.
No. There are 2. One will be cis, other will be trans. In even, both cis and trans can get created. Look at the intermediate. There is an intermediate, right? So this bond can rotate, and then when it is rotated, cis can become trans, trans can become cis. So it can create both cis and trans. Are you getting it? Now let's look at option number 3. CH3, CH, H, CH, Br, CH2, H. If I take out this hydrogen, this one, can there be cis and trans? If I take out this hydrogen, then it will look like this. Will this alkene have cis and trans? Why not? Because for cis and trans, on both the carbons, two different groups should be attached. Here, both of them are hydrogen only. So it will not show cis and trans geometrical isomer. Okay. So that is why if this hydrogen goes, only one product. But if this one goes, can it show cis and trans then? Now there will be two products. CH3, C, H, double bond, C, H, CH3. This is trans. And you can make cis also. So the answer is 3, not 4. Okay. Write it down somewhere that in even, cis and trans both can get generated. Okay. Next question. Tell me what product you will see. Delta is there, so elimination will happen. Even. Try. Then anybody? What will happen?
So would it be a cyclobutane ring with like C double bond CH and CH3?
Cyclobutane will remain as it is.
It forms a double bond with the
CH2 and then a single
Okay.
bond CH3.
Let us see that. Okay. First step is what? Carbocation will get formed. C plus CH3, CH3. Now this is a 2-degree carbocation. Can it become 3-degree? Possible? Or can this overall compound be more stable? If the ring expansion happens, if this alkyl shift goes to this carbon, if it shifts to that carbon, you'll see that this is CH3, CH3, and this. It has become a 5-membered ring. Positive charge will go there because this bond has been broken. So this carbon will attain the positive charge. So it's a 5-member ring now. Has anybody tried this ring expansion? You guessed it correct, anybody? That's okay. This is positive charge. Now, can this carbocation become more stable? Is it possible to be like 3-degree carbocation from here? Possible? Can I shift some hydrogen or something to make it a 3-degree carbocation? Anyone? Okay. This methyl, you can see, can shift, and this will generate CH3, CH3 plus. Okay. And now this hydrogen as well as this hydrogen are next to this carbocation that can be removed, and double bond can be shifted here or there. If you shift this one, if you remove this hydrogen, more substituted product will be formed. So since we're talking about a major product, the product that will get formed majorly is this. Anybody has any doubts? Please ask. Anything? Shall I proceed?
Yes.
So can you repeat the whole mechanism once more?
See, this is a carbocation that get formed. This is clear, I guess. Right? Then this compound, to gain the stability, ring expansion, whenever there is a chance, it will happen. 4-member ring is very strained. So there's an alkyl shift. There's a ring expansion that happens. So from here, this will get formed. And the positive charge comes here. Is it clear till here? Till here it's clear, no? How you know positive charge will go there? Because this bond has been broken. This bond has been broken for this carbon and for that carbon both. But for this carbon, one bond has broken and another bond has formed. But for this carbon, it is just that one bond is broken and nothing else happened. So for that carbon, positive charge. it has lost one electron, the positive charge. Then this is a 2-degree carbocation. And if you shift methyl, you'll get 3-degree carbocation. And that is why there is a 3-degree carbocation. And hence this product.
Yes, sir.
Okay. Any other doubt? Anybody? Nothing? Okay. Now this was even reaction with halides. Can anybody tell me how the even reaction will happen with alcohols? Carbocation needs to be formed. How it will happen?
So is it by adding
Adding what?
electron withdrawing groups?
No, that is not. Don't confuse with benzene. What we used to do with SN1 for alcohol,
You add H plus and then
add H plus. Exactly. Exactly. Okay. So for even mechanism with alcohol, it is already written above. For that, we will have either these, when these things are written H3PO4 slash heat, or second H2SO4 slash heat. Heat delta is important. You can see that whenever there's a heat or delta or written higher temperature, your mind should immediately think that there is an elimination that is going to happen. Okay. Otherwise, uh, substitution can also happen, right? And here, uh, there is no nucleophile as such. Okay. Just that H2SO4 and heat, the reaction will proceed with the elimination. Okay. But in the previous case, there was this, in SN1, H2SO4 was there, and then there was a nucleophile which attacks. Okay. Fine. So let's take certain examples. All of you do this. CH2OH. If you write concentrated H2SO4, okay, then you don't need to write heat also. Otherwise, H2SO4 heat. Let me write heat, so that you don't get confused. Anybody got it? Done? This carbocation will get formed. Then what will happen? Anybody?
So it will shift.
What will shift?
The positive charge will shift. One
Hydride
carbon
shift.
below.
Hydride
Yeah.
shift. This hydride shift will happen. Hydride is H minus, okay? H minus shift there. This becomes CH3. This is plus. 3 degree carbocation. From 1 degree directly it is becoming 3 degree. So that will be favored. Now hydrogen, the adjacent carbon hydrogen can be from here and can be from there. If it is from here, more substituted alkene will get formed like this. If it is from here, less substituted alkene will get formed like this. So this is major. Okay. Anybody has any doubts as such? Anything? Nothing? Okay, I'll give you maybe one more example. Do this. Done. See, these questions are not very straightforward. So in case you're not getting it, it's okay. But learn from it, okay? If I were a student, I may also be not getting it. So this OH will be gone and positive charge will be here. Do you all agree? This carbocation will be found. Now, can this carbocation, which is 2 degree, becomes 3 degree? Is it possible? Why not? Not.
So there's no adjacent hydrogen atom for the tertiary carbon.
No, even alkyl shift can happen.
Oh,
Right? You have these two alkyl, this one and this one. These two alkyls are there, isn't it? So which one will shift?
methyl.
Methyl.
It is ethyl that shifts. Okay. Always remember this migratory aptitude. Hydride is highest. Then phenyl is the highest. Phenyl hydride, though it is so little, because of its size, it can shift very fast. Then if alkyl shift has to happen, then 3 degree, then 2 degree, and then 1 degree. Okay. Let's not get into reasons every time. Just remember this. Okay. Now this alkyl will shift over there. And you have positive charge there. And there's a hydrogen here, which whose electron can create a pi bond, and more substituted alkene gets formed like this. Okay. Fine, I guess. Next question. These questions are more important in theory, okay? So you should be able to solve questions. So next question is this. This is well-known, famous question. Delta is there, elimination will happen. Are we done? Okay. सबसे पहले इसको first let me make it straight like this. So I will ask you only. This is CH2 plus. Now, what do you think should happen? Unmute yourself.
The hydride shift.
Hydride shift will happen. It will gain, this will help it gain much greater stability. Apart from being 3 degree, what else is special about that carbon? What
It's a
else?
conjugated system.
Conjugation.
It's a conjugated system. Double bond, single bond, positive charge is a conjugated system. Double bond, single bond, double bond, that is also conjugated. Double bond, single bond, negative charge, that is also conjugated. Conjugated, it's a cross conjugation from left hand side and as well as from the right hand side. Now, what do you think will happen? Let's see.
Yeah, can it have like a resonance and form a benzene ring? Something like that.
Okay. See, one product is that a double bond gets formed here only, right? That is one product. If I ask you next product, is there a possibility of another product? You can say, sir, there is a hydrogen here, adjacent carbon hydrogen, but then you can't have a double bond here. So that is why it can't take this hydrogen. And also it is allylic hydrogen, sp2 hybridized carbon hydrogen. That can't be taken just like that. So due to conjugation, you have to see what is the next possible structure. So when you shift it over here, double bond comes here, there's a positive charge now goes there. So you can see a 3-degree carbocation converts to 2-degree carbocation. But more than 2 degree, 3 degree, this conjugation is much better because it is continuous conjugation. Here it is what crossed. They are coming in way of each other. But anyways, that is not most important thing. The most important thing is the product is very stable because now it can take this hydrogen and form benzene ring. So you can see now this will get formed, right? That is most important thing. The product is so stable that once it starts getting formed, entire thing will move towards that only. Okay. Okay. One last question before we go to E2. E2 is a small this thing.
Sir, so the previous question, it has two products formed or just one?
Very little amount of this product will get formed
Okay. Understood.
because the second product is so stable that almost entirely will be. But then suppose there's a question, what will get formed? Only one option is correct. Then you have to choose the major product only. Okay? If they ask you write down all the products, then you have to write all the possible products, right? And then you have to also see cis and trans. Cis and trans are possible only when you'll have two different groups attached to this carbon and two different group. If let's say these two groups are same, if these two are same, no cis trans. These two should be different. It should be XY here also, or here could be YZ or something. It can't. These two cannot be same for cis and trans, which we have done in the GOC in detail. Okay. Anyways, CH2OH, CH3, you have H2SO4 concentrated. Concentrated H2SO4 is a great dehydrating agent. I mean, you don't need to write heat with alcohol at least. Done? First carbocation will be this. Then what will happen? This hydride will shift. So you'll have CH3 plus. Now it can take hydrogen from this carbon as well as from that carbon. From where it will take more, A or B? Hydrogen it will take from A or B?
From B.
B will create this alkene. And if you take from A, this alkene will be created. So where it will take, A or B? This is from A, this is from B.
So would it be A?
It'll be A. More substituted alkenes are always preferred if it can get formed. So in even, more substituted alkenes will get preferred. Things will go towards more stability or thermodynamic. Thermodynamics will drive here. Kinetics will not drive, or entropy will not drive situation here. Okay, so I'll move ahead to E2 now. So this is E1. How do you identify whether it is E1? There's a delta sign, or concentrated H2SO4 is written. Concentrated H2SO4 for the for alcohol. Okay. For halides, it is always delta sign with a weak nucleophile. E1 will happen. Okay. Now we'll write down E2. E2, just like SN2, is a bimolecular, write down, bimolecular reaction, elimination reaction. Okay. So again, here it is beta elimination that we'll be talking about. Beta is what we discussed. Uh, Beta is what? The alpha carbon is what? Alpha carbon is the carbon in which leaving group is attached, in which halogen or OH group is attached, that is your alpha. Beta is what? Next to the alpha. Next to the alpha could be left hand side or right hand side. Okay. So that is, it can have, let's say, 2 or 3 beta carbons, alpha. Alpha can have 2 or 3 beta carbons. So this is leaving group, this is hydrogen. It'll create carbon-carbon double bond. This is what we have learned in E1 also. What is so special in E2? In E2, everything happens simultaneously. It's a bimolecular elimination. Just like in SN2, the reaction depends on concentration of the nucleophile as well as the substrate. The rate determining step will have both together in SN2 as well as in E2. In SN1 and E1, rate determining step has only substrate. Nucleophile doesn't come in the rate determining step. If you increase the concentration of nucleophile, rate will not get affected for SN1 and E1. Okay. Now coming to E2, let's see the typical mechanism. This is H. Now everything is happening simultaneously, and here instead of calling it a nucleophile which attacks, we call it base. It is better to call nucleophile as base since it attacks H instead of carbon. If it attacks carbon, then you say nucleophile. Why will you say nucleophile when it takes H plus? H plus is taken typically by the acids, sorry, base. So we'll call it base. So this base takes this H and it just takes H plus. There are two electrons here which are creating the bond. These two electrons will go there and start creating the pi bond. And this leaving group will take its lone pair and leaves. And all of this happens simultaneously. Okay. And then, this carbon-carbon double bond gets created. Okay. So if you look at the transition state, it is somewhat like this. The base. This is bond formation. This is bond breaking. This is bond formation. This is bond breaking. So bond formation, bond breaking, everything is happening together. Okay. Now let's write a couple of points, then I'll come back to the stereochemistry of it. Write down E2 reactions. Do you think this E2 reaction can happen with uh, alcohols, OH? Can it happen with that? Can OH leave like this? OH cannot leave like that. So with alcohols, you have to catalyze, and when you catalyze, it becomes even. So with alcohol, E2 will not happen. You need good leaving group, which can leave on its own. When base attacks, it can leave. Okay? When the base attacks, you can't have acid and base together in a mixture and then you'll be like, okay, base will attack hydrogen, acid will catalyze the alcohol and then good leaving group. It doesn't happen like that. Okay? So please write down E2 reaction needs good leaving group. It need not be halide though, need not be halide, but typically it is halides because halides are good leaving groups. Halides are good leaving groups. Fine. Because Br minus such a big size bromine, iodine, they are big in size. And so if it is a negative charge will spread in entire volume and it becomes stable. That's why it is a good leaving group. Okay. So what are the reagents here? What kind of base are there? Please write down hot reagent that will be written for you to understand that E2 is going on. Hot alcoholic, hot alcoholic solution of KOH. Alcoholic is what? A polar protic or polar aprotic?
Polar aprotic.
Alcohol are aprotic. They are protic. They have a hydrogen attached to the electronegative atom, okay, which is oxygen. Or you can have, let us say, ETO minus in ETOH. Okay. You can have MEO minus in MEOH. MEOH is what? MEOH is solvent. MEO minus is a salt. MEO minus salt dissolved in MEOH. Can you dissolve MEO minus in ETOH? You can dissolve तो हो जाएगा. But now you have two nucleophiles or two bases. ETOH will also do something and MEO minus will also do something. So you can have multiple products. So that is why ETO minus in ETOH or MEO minus in MEOH. Okay. Or simply you can take hot alcoholic solution of KOH. That also will do. You need a very strong base, NaNH2. NH2 minus is extremely small, extremely strong base. NH2 minus can take the H plus and become ammonia. Then you have these kind of bases like tertiary butoxide in tertiary butyl alcohol. Okay. Fine. Is it clear to everybody? Clear, no? Okay. Now, how it is different from SN2? How will you recognize whether substitution, bimolecular substitution will happen or bimolecular elimination will happen? How will you know? Looking at the reaction. I told you already.
So here you need a base.
Good leaving loop.
There also everything was that way only. But only one thing that you'll see is heat. In all the elimination reaction, heat is one thing which favors the higher entropy. And elimination will go on. Of course, these reagents are also important, but most important thing is heat. If heat is not given at room temperature, substitution is preferred, elimination is not preferred. In SN2, just a strong nucleophile is needed. In E2, strong nucleophile plus heat is needed. Both. Okay. I hope it is clear to all of you. Now, let's talk about stereochemistry, as in what happens to how it attacks, at what angle it attacks, what should be the geometry so that E2 happens and stuff. Okay. So let's take this thing. This is a leaving group. This one. First of all, you can see there are 4 atoms written here. You have hydrogen, carbon, carbon, and the leaving group. So all 4 atoms HCCl should be in the same plane. That is the first requirement. Okay. Fine. First thing. Second is L and H. There could be many H. I'm talking about the H where the base will attack. Hydrogen where the base will attack. I'm talking about that hydrogen. That hydrogen and L, they should be, I'm telling in a very crude way, they should be like 180-degree away. If leaving group is down, hydrogen should be up. The reason is pretty simple. The base has a lone pair. Leaving group also comes out with a lone pair. So they will repel each other. So base will attack however much away it can from the leaving group. Right? So H and L are 180-degree away from each other. Fine. How will you know it is 180-degree away from each other? Have you seen this kind of projection? This is the same compound. I can write like this. If you see this kind of projection, this is L and this is H, then it becomes very simple. You know that is 180-degree away from each other. Here also it is evident, here also it is evident, here also it is evident. But when you write like this, Newman projection, sorry, this is Fisher projection. In Fisher projection, it is not straightforward. So you need to either convert it this way or this way. Then E2 reaction you have to check. Okay, you'll see when you'll have the reactions. Okay, please write down couple of points. Point number one, the rate of reaction depends on concentration of base. I'll write like this. Rate is equal to constant times base as well as the substrate. Same thing was with SN2 as well. But instead of base, we were calling it nucleophile because nucleophile attacks carbon, base attacks hydrogen. Okay. Second point is rearrangement cannot be possible. Rearrangement is not possible. There is no formation of carbocation itself. Forget about rearrangement. Okay. That is second point. Third point. Write down. Acha, I also have to write down. No rearrangement. First, second, third. If bulky base like tertiary butoxide is used, then the hydrogen comes out from less crowded carbon, leading to less substituted alkene. Bulky base is like, tertiary butoxide. How does it look like? I'll show you. This is tertiary butoxide. Okay. Now imagine this attacks something like this. CH3, C, CH3, CH3. Wait. C, Br, CH2, CH3. Now look at this hydrogen and this hydrogen. So this base will attack which hydrogen? First one or the second one?
First one.
First one. So it can't go to the second. It is so bulky itself. So even though most substituted alkene is more stable, but here because of the steric hindrance, this alkene will be the major product. Less substituted will be major product. This happens with the bulky one. Tertiary butoxide, whenever it is there, you have to be careful that most stable alkene doesn't get formed. Less hindered alkene gets formed. Okay. Okay. Fine. I hope it is clear. Okay. Now tell me, now we'll solve numericals. Okay. We are done with both E1 and E2. Whatever time is remaining, couple of numerical, and then we are over. Done. Suppose this is your chlorine. Okay. Here hydrogen. Here hydrogen. Okay. Now you are using the alcoholic KOH and heat. What will be formed? Which hydrogen it attack? First tell me that. The first one or the second one? Which hydrogen it will attack? Alcoholic KOH.
First one.
Second one, right, sir?
Which hydrogen is 180-degree away from the chlorine? First or second?
First one.
First one.
First one, so it attack first one. Suppose, now hypothetically speaking, 180-degree opposite hydrogen is not there. All the hydrogen are towards the side of the chlorine. Then it will not be able to attack only. Nothing will happen. It must have a hydrogen. You can write it down. It must have a hydrogen which is like 180-degree away from the leaving group. Must for E2. Okay, so the alkene will get formed. And this hydrogen and this chlorine, oh sorry, chlorine is gone. This will happen. Okay. In fact, it is since it is sp2 hybridized, then you don't need to draw wedge and dash with sp2. You can say that it comes in the same plane. This is the hydrogen. But what is gone is this. This one is gone. Okay. Uh, Next, I have a theoretical question. Carefully listen and answer. Okay. Correct statement for E2 reaction is it is a two-step process. It is a unimolecular reaction. Strong base favors. Carbanion is formed during the reaction. Which one?
Strong base pairs.
And what about unimolecular?
That's a bimolecular reaction, right?
It's a bimolecular. Two molecules are involved. Okay. So only that one statement is correct. Okay. Then,
So I have a doubt.
hmm,
So you had mentioned that all four atoms, the H, both the C and L, must be in the same plane,
hmm,
right? And if they're in the same plane, we have to
hmm.
take the dashed wedge, right? Because
Ah,
the leading group and H should be in the same plane.
correct.
If
Same,
taking the solid and the dash, they're not in the same plane.
they are in the same plane. Let's say this one line is going up, one line is going down. I can have a plane like this, which will have both lines going up and going down. So my plane is going like this, and it covers whatever is above as well as whatever is below. Got it?
Understood, sir.
Uh, which of these cannot? But then, anyways, the most important point is the hydrogen and the leaving group. They should be 180-degree away from each other. Always, always. If that is not there, reaction will not happen. Okay. Which of these cannot undergo E2 reaction? I'll write down this. Hmm. Answer. A, B, C, D. Which one?
Will it be C?
Reason?
There's no hydrogen present.
Okay. All of you agree? There
Sir,
is
I
no.
thought it was D.
Why it has no? It has two hydrogens here. You need beta hydrogen. Here, look at this is the carbon from where the bromine will come out. Adjacent to it, only one carbon. Does it has? Does it have any hydrogen here? There's no hydrogen. So no point talking
Understood.
about that will come out. So you need
Understood.
a beta hydrogen. Otherwise, nothing will happen. Okay. Now tell me rate of reaction here when you talk about halides Ri, RBr, RCl, RF, which one will give the highest rate of reaction in E2? Obviously, the leaving group should leave easily. So this, in fact, the carbon to fluorine bond is very strong. So it doesn't fall under E1 or E2. We with RF, it is a different thing altogether. Okay, but it is slow. Rate is slow, so that is why we can include it. Clear? I hope it is clear. Okay. Now let's talk about rate in terms of 3 degree, 2 degree, 1 degree alkyl halides. For elimination E2, which one will have the highest rate? You remember SN2, which one had the highest rate? 3 degree, 2 degree, 1 degree?
1 degree.
1 degree. Over here, what? Over here also you expect something
1
similar,
degree. Yeah.
but that is not true. Over here it is 3 degree, 2 degree and 1 degree. This is little counterintuitive, but if you understand clearly how substitution happens, this is R1, C, R2, this is leaving group, this is R3. Nucleophile comes, attacks the carbon, and the leaving group leaves. But over here in elimination, what is going on is this. The base is coming, it doesn't attack 3 degree carbon. Here in substitution, nucleophile has to attack 3 degree carbon. In elimination, base attacks the carbon next to the 3 degree carbon. It has to take hydrogen from the adjacent carbon. Getting it? Is it clear? Right? And then this bond is getting broken, and then what else? Maybe this bond is getting formed. So hyperconjugation is getting created. So more, it is a 3 degree carbon, so it can stabilize this intermediate that get formed in a better way. So crowding doesn't affect it so much. Even though it is a 3 degree halide, it doesn't have to go and attack the 3-degree carbon in elimination. It has to attack the carbon adjacent to the 3-degree carbon. Clear? So please remember, this is something which is different from the SN2. Everything else is very similar, but when it comes to the rate of 2-degree, 3-degree, this is different from the SN2 if you compare E2 and SN2. Now, one last thing is the energy diagram. How many transition state you have here?
One, sir.
One. Do you have any intermediate? That an intermediate compound is created like a carbocation? No. No intermediate means only one transition state. One intermediate has two transition state. Two intermediate will have four transition states. So there is no intermediate. So it's a straightforward curve like this. This reaction right now I'm showing it to be endothermic. It can be exothermic also. But since we are providing heat and it is kinetically favored, not thermodynamically favored, typically we assume elimination to be endothermic. So that is why when we show endothermic, product slightly above we draw. Okay. But it need not be endothermic all the time. This is the transition state, the main transition state that is there. Okay. Right. So that's it for today. I will share some assignments. We have done substantial amount. Now, unfortunately, yesterday class got cancelled. Otherwise, we would have completed the mechanism by now. But was addition mechanism done in your school or only substitution and elimination was done?
Only substitutions.
The elimination was not done.
We did
No.
do elimination. We did substitution and elimination.
But addition was not done. Okay, so what we'll do next class, we'll quickly finish the addition and straight away jump to the alkyl halides. Now alkyl halide, I mean, can you able to relate to your school, what you did in alkyl halides? More than 50% is already over. Right, so now we'll move faster. And every time when we do the chapter, I'll keep reminding you that this mechanism we have seen, this mechanism we have discussed, like that we will proceed. Okay, so that's it for today. I'll share the assignments. Okay, bye.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir.